Well, good day, everybody. This is Chris with the Ancient Scholar. I hope this video finds you all doing well. And I'd like to pick up where I left off talking about STEMI mimics. I know it has been some time since I've done a video on that, and I do apologize for that. I've been heavily involved in training for an upcoming endurance mountain bike race. It's a 10-hour race that I'll be doing in just a little under a week. And so I have been training for that. I sold one of my bikes. I bought a new mountain bike, a trail bike. I've been having a lot of fun with that. So I've kind of been devoting all of my free time into those areas and activities and have neglected the more academic nature of what I do on this channel. I'll put quotes around academic, of course. But I do want to talk a little bit about STEMI mimics in the next content area I want to cover is using Sgarbossa's criteria. Specifically, I'm going to be talking about modified Smith's Sgarbossa criteria because I feel it is a little more intuitive and it is a little easier paradigm to work with. So with that in mind, let's build some foundation for understanding what modified Smith-Sgarbossa criteria is and why and how we use it. So first, this is really in reference to two major findings. This is in reference to the presence of a left bundle branch block and ventricular paced rhythms. The reason that's so substantial is in those two instances, you tend to have grossly abnormal depolarization, right? You're talking about a left bundle branch block where the left bundle branch is not working, and so everything goes down the right bundle branch, and then you get retrograde conduction of that wave of depolarization and it coming up through the left ventricle in kind of a retrograde manner. And so you have slowed conduction, you have these wide, bizarre-looking QRS complexes, and the same with ventricular paced rhythms as well, or essentially the same thing. You're having this abnormal depolarization occurring. And the general rule of thumb is, if you have abnormal depolarization, you should have abnormal repolarization, all right? And so this creates a situation where you're going to have substantial deviations of the T wave and the ST segment because of that abnormal repolarization that you will find in left bundle branch blocks and ventricular paced rhythms. And this produces a characteristic or classic finding known as appropriate discordance. What is discordance? Well, discordance is when the QRS complex and the T wave, or the ST segment and the J point, are moving in opposite directions. So to understand discordance, let's first understand concordance, where everything moves in the same direction. And we see this in a normal PQRST complex. So I've gone through the liberty of drawing one. So you've got the P wave, the QRS complex, and the T wave here. And this is more or less normal. And you can see that the QRS complex is upright and the T wave is upright. And this would be what we call concordance of the QRS complex and the T wave. They move in the same direction. Now, in the setting of ventricular paced rhythms and left bundle branch blocks, you should have what's known as discordance rather. We call this appropriate discordance. So here's an example of that. So this is a left bundle branch block. So you see this wide QRS complex here, and it is negatively deflected in this specific lead. And then you have the T wave, which is positively deflected. So it is going in the opposite direction as the QRS complex. The QRS is going down, the T wave, the J point, the ST segment are going up. And you see that this produces elevation of that J point above the isoelectric line. So this produces ST elevation, which may be mistaken for ischemic or injurious findings, the current of injury. Likewise, we see this with pace rhythm. So here I've got a pacer spike, I've got a wide QRS complex. In this case, the QRS complex is deflecting upward. And then I've got the ST segment a T wave, J point deflecting downward. In both cases, the QRS complexes and the T waves are moving in the opposite directions, or deflecting in the opposite directions, and this is what we refer to as discordance. Now, when we are analyzing ventricular paced rhythms and left bundle branch block specifically for the presence of an acute coronary syndrome, we need to take this into consideration. And now that we know that there is this appropriate discordance, we need to understand, well, how much is appropriate and what are deviations from this appropriate discordance pattern that point us in the direction of thinking about ischemia, injury, and infarction. And that's really what the modified Smith-Sgarbossa criteria aims to do, is to give you some tools for analyzing these rhythms and looking at them and going, okay, yes, there's a bundle branch block, yes, there's a ventricular paced rhythm, but are the findings outside of what we would normally see, and does that suggest that there is the presence of ischemia, injury, or infarction?